Okay, so far we've been looking at electric fields, and we've looked at point charges, we've looked at multiple point charges, and we've looked at spheres, both inside and outside of conductors and insulators. And so what we're going to do now is we're going to start looking at the electric fields around other objects. And that chart that you have, we're going to start filling in more and more. You're not filling in the formulas, you already have those, but it would be a good idea to go through and take drawings in that last column so you have a visual to help you out a little bit. Charge distributions. First one that we're going to look at today is dipoles. A dipole is basically you've got a positive and a negative charge, that's it. And we're going to come up with a formula for being along a certain line, depending on where you are, what the electric field is there. We also have continuous charge distributions. We are going to talk about infinite lines, infinite sheets of charge, which is kind of weird. Infinite, we wouldn't have that, but we want to know what would it be like theoretically to help us out with some other calculations. You know, we can think of a very large thing. Rings of charge, and so we also need to think about charge distributions in terms of linear charge distribution, surface charge distribution, and volume charge density. Sorry, so we're looking at charge per line, so coulombs per meter. Also, sigma, right, coulombs per meter squared, and volume charge density rho, coulombs per meter cubed. And so let's take a look at an electric dipole. Electric dipole, again, it's a pair of charges. They're a distance d away, positive and negative q. And the quantity qd is actually its own quantity. It's called the dipole moment. And it's abbreviated p, like momentum, right? P for momentum. Except that it's the dipole moment. It has magnitude qd, and it's in the opposite direction of the electric field, right? It goes from negative to positive. All right. Now let's take a look at the derivation for the electric field due to a dipole. Okay, so we're going to look at the electric field due to an electric dipole and derive the formula for it. Now, realize we're talking about this along this line. We're not figuring out the formula, for any place here. So let's familiarize ourselves. A is half the distance, D is the distance here, and Y is the vertical distance away from these two. Now, the electric field due to this charge here is going to be away. A positive charge, it goes away. But towards a negative charge, it's going to go that way, right? And these are equal to each other in magnitude at least, so that's kq over r squared. And then what's that distance? What is r? Well, it's the square root of a squared over y squared. And we square that, right? And so in the denominator here, it's just a squared plus y squared. Okay, using that, now we can figure out this is going to be the horizontal component. This is going to be the vertical component here. For the positive, this is the negative. These two are going to cancel out. And so we're simply left now with 2kq a squared plus y squared cosine of theta. Okay. In the I direction. But remember, cosine is a over the square root of a squared plus y squared. And so when we plug that in, now we end up with this thing, 2kqa over a squared plus y squared to the 3/2, and including the vector unit I hat. And so that's it. This is our formula. That is the electric field due to a dipole along the axis, along the bisector of the dipole. All right. And what if y is a lot bigger than a? Then in that case, the electric field is just kqd over y cubed. Right. And so realize here these distance units cancel out. Okay, so now we're going to look at this along the axis of the dipole. Right? Before we were along the bisector, now we're looking along the axis, some distance y from the midpoint of the dipole. So here's the dipole, here's the midpoint, this is the distance y. The distance from here to here then, or rather from here all the way down, is y plus a, because remember a is half of the distance between the two charges. Okay, and so again, E total, we're going to add these up. KQ over R squared minus KQ over R squared of the negative charge, and then J hat, right, because we're looking along the J component here. Now, the 1 due to the negative is going to be less. The electric field due to the positive is going to be more. So that makes sense. So E total, we're going to add these up, right, which is really subtracting because this one is negative. It creates a negative electric field there. And we can factor out KQ. And now we can look at this as a product of two squares, factor it, and then we can try to get common denominators for each of these. So we end up with y plus a minus y minus a. Simplifying, we end up then with this. And so we end up with 4kqya over y squared minus a squared, all of that squared. And what if y is much, much, much greater than a? Well, if y is much greater than a, this a kind of disappears down here. And so we get y to the fourth, and then one of these y's cancel out, and we get y 4kqa over y cubed. Right. So here are the general electric field equations for any continuous charge. First we break it up into tiny charge elements, delta qi, and then we're just adding up if we're looking at a continuous charge distribution. So we can think of it this way: the electric field is the total of all of these things added up, and we're looking at the tiny pieces of charge going to zero. Right? This looks like calculus, and so it is. Right? As these things go to zero, well, then we're taking an integral dq over r squared. dq depends on the geometry of the charge. If we're looking at it as a line, then it's lambda ds dq is lambda ds or lambda dx, right? S and x are our position notes, and so dq is sigma dA for an area of charge if we have an area charge distribution, or if we have where rho is the volume charge density, dq is rho dv. And then that'll determine what we put in here into that integral when we try to find some electric field. So let's take a look at our first one here. This should kind of look familiar, right? We've seen something like this before with gravity. And so we're going to find the electric field at this point due to a line of charge, a uniform finite rod of charge here. The total charge on it is Q, the length is L, and uniform charge density lambda. So remember, lambda is the charge density, so it's the amount of charge divided by the length. And so lambda is Q over L, or delta Q over delta X. X is on the horizontal axis here, so we're going to use X in this. And so then delta Q is lambda dx, and Q is lambda dl. And since it's a positive charge, E field here is going to point to the left. And if delta X is small, we can consider its charge, delta Q, to be a point charge. Right? We're breaking this up into tiny, tiny little pieces here. All right, so delta E then is K delta Q over R squared, but R is really X in this geometry. And so we've got K delta Q over X squared. Delta Q then is L delta X from our previous set of slides. And X goes from D to L plus D. All right, so what it looks like we're setting up here for an integral, right? And so the total electric field is going to be from D to L plus D, K L delta X over X squared. All right. And so the K and the lambda come out front, dx over X squared, so we can look at this as X to the negative 2. You can use the quotient rule, or you can look at 1 over X squared as just X to the negative 2. And then when you take the integral, you get k lambda negative 1 over x from d to L plus d. Now we just plug in and simplify, try to get a common denominator here, and we can do that this way. And so E is, the electric field comes out as k lambda L over d L plus d, but lambda L, right, because lambda is the charge density of the line, multiply that by the length of the line, you end up with the total charge. So it's just kq over dl plus d. And what happens if d is much, much less than L? Well, then you end up with kq over, if d is much, much greater than L, sorry. If d is much greater than L, then down here you just end up with d squared, so it's kq over d squared. And that makes sense. If you get really far away from this thing, it's as if this is just like a point charge, right? kq over r squared, or d squared in this case. And what if lambda is not constant? Well, then in that case we have a lot more work to do, and we are not about that life right now.